Great, Gao. Thank you so much for the introduction. I'm assuming you can hear me. You can see my screen. Yes?
You can see your screen.
Okay. Yeah, thank you so much for the kind introduction, and thanks for putting together such a nice tutorial. I attended the entire event, was very, very interesting. So thanks for the effort. I'm Luca Carlone. I'm an associate professor at MIT, and today I'm going to share this presentation with Rajat Talak, who is a postdoc in my group. In particular, today we're going to tell you about hierarchical 3D scene understanding for robotics and to draw connections with graph neural networks. This, by the way, is also working in collaboration with the students in my group that you see on the slide, Nathan, Yoon, C, and Lisa. Okay, so I will start by saying that high-level 3D scene understanding is a grand challenge for robotics and is about designing algorithms and systems that allow a robot to use sensor data to understand the geometry, semantics, and relation among elements in a 3D scene. 3D scene understanding is crucial for a robot to parse and execute high-level commands from a human. For instance, if I want to ask a robot, go grab me the cup of coffee on the table in the kitchen, in order to parse and execute this instruction, the robot will need to have some information about geometry. We need to know, for example, where is the kitchen? We need to know about semantics, right? We need to know what is a cup of coffee. And we'll also need to parse relations. What does it mean for a cup of coffee to be on the table and for the table to be in the kitchen? So high-level 3D scene understanding is key to interaction. Not only that, 3D scene understanding is also key to robustness. In particular, when we parse a scene as humans, we do not parse objects in isolations, but we reason over the context and relation between nearby objects. For instance, in this image, we understand that this one is not a physical car, is a car which is painted on a billboard. And this is because we reason holistically over the scene and we can understand the relation between this part of the scene and the surrounding elements. This instead is a problem for real robotics application where the lack of scene understanding, or if you want, the lack of common sense, leads to perception failures. If you don't believe me, you can easily find a couple of examples from self-driving cars with failures of current perception systems. This is a fairly recent one, is a Tesla autopilot. And you can see at the beginning of the video that there are a set of traffic lights on top of the truck. The perception system of the Tesla vehicle in this case fails to reason over the relation between the traffic lights and the truck, which leads to an incorrect interpretation of the scene. Therefore, our work here addresses the question, can we develop algorithms and perception systems that allow our robot to understand 3D scenes, including geometry, semantics, and relations? So today I'm going to argue that 3D scene graphs are a particularly effective representation for 3D scene understanding. In particular, in the first part of the talk, I will present our definition of 3D scene graphs, and I will introduce real-time algorithms that are able to create the different layers of a 3D scene graph. That's the work on the left. And then I will pass it to Rajat, who is going to tell you about how to use graph neural networks to perform inference over 3D scene graphs. And Rajat is also going to introduce this idea of neural trees. So let's get started with the idea of 3D scene graphs. So what are 3D scene graphs? Actually, this definition you will see is slightly different from the definition that you have seen in previous presentation. 3D scene graphs are nothing else than a new map representation for robotics. In particular, a 3D scene graph is a hierarchical model where at the bottom there is a 3D mesh with semantic annotation. So you see the 3D mesh. Each phase of the mesh comes with a different color, which corresponds to a different semantic label. And if you go up in the layers, if you go up in this hierarchy, you essentially abstract away the mesh into high-level semantic concepts, such as objects and agents, places and structures, rooms, buildings, and so on. So many of these layers are pretty easy to understand, right? You know what is a room, you know what is a building, you know what are the objects. The only layer that requires a little bit of an extra explanation is layer 3, which is the layers of places and structures. So structures are just the walls, ceiling, and ground within an indoor building. Instead, places are obstacle-free locations the robot can go to. So imagine that you have a graph of places in which each node in this graph is a location the robot can reach, and edges represent traversability between different locations. In other words, places are just representation for the free space in the environment. So more formal, a 3D scene graph is a directed graph where nodes correspond to spatial concepts, which is really anything living in 3D, and edges represent spatio-temporal relations between concepts. For example, agent I is in room J at time t. The reason why we believe that this representation is very powerful for robotics is threefold. First of all, we can represent, through the edges in this scene graph, we can represent relations. And we have already seen in previous talks how powerful it is to represent relations within elements in the scene. Second, 3D scene graphs, our definition of 3D scene graphs is really unifying a lot of different map representations for robotics. For example, the 3D mesh is what is called a metric map in robotics. Layer 2, the objects correspond to what is called the landmark-based map in robotics. And the graph of places is what is called a topological map in robotics. So now you have all these representation unified in a single model, in a single 3D scene graph model. And finally, of course, this 3D scene graph includes actionable information for planning and decision-making. Now the robot knows about rooms, objects, and relations, therefore can understand and execute high-level commands, such as go to the kitchen and grab me a cup of coffee, for instance. So let me contextualize a little bit our model among some related work, including those that we have seen today. First of all, we have to realize that the idea of hierarchical maps is not new in robotics. And even in early works, you can see a lot of discussion about how to combine topological and metric maps. However, this representation, including the spatial semantic hierarchy that you see on the left, essentially were proposed very early on, like 2000 or even before then. So they are missing the rich semantics we can now afford with deep learning. If you look at the second work, that's the scene graph, the original scene graph paper by Hydra. So this representation is quite similar to ours, but is missing key layers that we need in robotics. For example, the places layer, which is something we use for robot navigation, is not there. Moreover, the focus for this original scene graph paper was more about visualization and offline construction of the scene graph. Instead, we're shooting for building these representations in real time on a robot. Third line of work, there is a lot of work, recent work in robotics about proposing other representations which are combining geometry, semantics, and relation. But again, this miss high-level semantics such as rooms, buildings, and so on. And finally, we've seen today the excellent work from the group of Federico and collaborators, which also targets real-time construction of scene graphs, but is focusing on objects and relations. And in a sense, our work is very complementary to theirs, in the sense that we focus on simpler relations somehow, but at the same time, we put more emphasis on the construction of rooms, buildings, and reconstructing the topology of the environment for robot navigation. So what I want to do next is to tell you a little bit about the algorithms we use to reconstruct 3D scene graphs. And I will start from early contribution for the first system that we provided to construct 3D scene graphs, which is called Kimera-DSG. Kimera-DSG stands for Dynamic Scene Graphs. So Kimera-DSG is taking input data from just a standard camera and inertial sensors, and is building layer 1, which is the metric semantic mesh using Kimera, which is an open source library that we proposed. This open source library is essentially taking camera images and 2D semantic segmentations, and in real time is transforming these camera images into a 3D metric semantic mesh, which is a 3D model where each phase of the mesh, again, is color-coded by a semantic label. So that's layer 1. On top of Kimera, what we do is to extract different objects. So after we have this metric semantic mesh, we extract the different objects in the mesh, which at this point is quite easy. We just, for example, isolate the vertices in the mesh corresponding to the label chair, and we can just isolate these vertices, do some Euclidean clustering, and fit a bounding box. Or if you have a CAD model, we can even fit a CAD model to different objects in the scene. And that's layer 2, which includes the objects. Then what we can do is reconstruct layer 3 and 4, which are the places and rooms. So what we do here is to reconstruct a volumetric representation of the map and extract a graph of places and the corresponding rooms by computing what is called a generalized Voronoi diagram. So if you're not familiar with this term, we essentially just extract a skeleton of the voxel-based representation, which is called a generalized Voronoi diagram, and we convert that into a graph describing the topology of the environment. And then we segment out this graph into different rooms. In our original proposal for Kimera-DSG, we're even able to extract dense meshes of humans moving in front of the camera. So while building the map representation, we could extract and track these dense models of humans in the environment. So with Kimera-DSG, we could do pretty fancy reconstructions of large-scale environments as the one that you see over here. But there was a catch. The catch is that the reconstruction that you see took around 30 minutes to reconstruct, which in robotics is not very useful. We like something that is understanding the environment in real time. And in particular, what happened is that the extraction of the places layer and the rooms required building a monolithic voxel-based representation of the entire environment, which made things very slow. And more importantly, since the trajectory and the mesh change after what is called loop closure, after the robot is making loop closures, this approach will need to rebuild a scene graph after every loop closure, which is again impractical. So today I'm happy to introduce Hydra, which is a perception system, a new perception system that we proposed. It's going to be presented at RSS next week, that can build a hierarchical 3D scene graph from sensor data in real time. So you see in the video that the robot is starting in a completely unknown environment, is incrementally building this 3D metric semantic mesh, is reconstructing its own trajectory, is populating the graph of objects in the environment, is extracting a topological map of places, which again form a skeleton of the environment, and then clustering this graph of places into rooms and buildings. So there are several insights behind Hydra. First of all, what we did is to realize that extracting a topological map, we can extract a topological map of the environment on the fly during mapping, instead of post-processing a monolithic voxel-based representation as in Kimera. So in hindsight, we realized that the topological map is something that we can get for free when doing mapping and reconstructing the 3D mesh. Second, we can reconstruct the graph of places, and we can segment the graph of places into rooms just by fast community detection methods, which are treating the graph of places as a graph and doing clustering on this graph to isolate the different rooms. And in hindsight, we realized that we never need to create a monolithic voxel-based map of the environment, which again would be incompatible with long-term operation. So this slide shows an example of Hydra running on a real data set and building a 3D scene graph. At the top left, you should see the images collected by the robot. These are 2D semantic segmentation produced by a standard 2D pixel-wise segmentation network. And then you get the 3D scene graph and the corresponding top view of the scene graph. And the slide also mentions two unique features of Hydra. First of all, since we have a scene graph, in the RSS paper, we also show that we can define hierarchical descriptors for loop closure detection. Intuitively, these descriptors can inform loop closure detection with information about other layers in the scene graph, including rooms, objects, places, and topology, making loop closure detection much more effective. Moreover, we developed a technique to simultaneously deform all the layers of a scene graph in response to loop closures. So we're able to correct for drift and enforce loop closures by doing a single optimization over the scene graph. So let me play this video again because there is a lot of information here to unpack. Imagine that the robot is starting on the first floor of this building, then it's going up to the second floor, is moving across the second floor. And you can see just visually that the room segmentation roughly is making sense, right? These places in blue are one room, the other places in green are another room. But you can also see that as the robot goes, the trajectory estimate is accumulating a little bit of drift, right? So the map reconstruction is drifting, which can be also seen in the top view image. At the same time, when the robot is coming back to the original location, there is a loop closure. And with this 3D scene graph optimization, we can correct in a single optimization run the entire 3D scene graph, which is pretty cool. So, of course, like, this is a robot, talking about robotics application. We are also in the process of testing Hydra on real robots, running on board on real robots. So these are preliminary experiments we did with Uni3A1, which is this guy at the bottom left. Again, you see the images from the robot, segmentation from a standard network, and the corresponding scene graph being created in real time. These are very preliminary results. That's probably the first test we did with this robot. But a couple of things that you can notice is that even though the segmentation is not great, the overall reconstruction of the map, the 3D metric semantic mesh is pretty accurate. We can get a nice reconstruction of the trajectory. And overall, the segmentation into rooms is hard to judge, to be honest, but at least the approach is doing something in this early test. I think the most encouraging bit of this slide, more than the reconstruction that can be largely improved, is the timing result that you see at the bottom right. This is the timing it takes to construct the scene graph on Xavier NX, which is an embedded computer. And you can see that you can reconstruct the graph of places, objects, and rooms in a matter of milliseconds. So this is something that we can easily implement. We can implement right now on a robot. Before passing it to Rajat, it's worth mentioning that 3D scene graphs provide incredible challenges and opportunities. For instance, the hierarchical structure of 3D scene graphs allows speeding up planning. In particular, on the left, we've been showing in our IGARR paper that we can use scene graphs to speed up planning by 2 or 3 orders of magnitude as compared to planning over voxels. Second, we've been showing that we can use graph neural networks, and that graph representations such as 3D scene graphs open the door to high-level reasonings and reasoning over high-level semantics. For instance, as humans, we can easily infer which type of room we are in by observing the objects within the room. For example, here, if the objects are bed, book, clock, and so on, we can easily infer that the corresponding room is probably a bedroom. And Rajat is going to tell you that we can do pretty much the same thing for our robots using a graph neural network. And finally, we have initial evidence that we have been presented at TICRA a few weeks ago that high-level representations such as 3D scene graphs can also boost performance in reinforcement learning-based navigation. And of course, there are many, many other applications such as monitoring, prediction, long-term autonomy, and so on. So now I'll pass it to Rajat, who's going to tell you about the work we've done in connecting 3D scene graphs with probabilistic graphical models in graph neural networks. And he will introduce this idea of neural trees. So let me stop the screen share. And Rajat, the floor is yours. Can see the slide. We cannot hear you yet. Now we can see you, but we cannot hear you yet. Nope.
Hello?
Now it's getting better. Try to speak. No.
Okay, does this work?
Yes. All right.
Okay.
And remember to share again, share screen again.
Yeah, I'll share the screen. And there's some problem with the audio. Okay. So sorry about that. Okay, so Luca discussed about how we have a system now, which is Hydra, which helps us build 3D scene graphs in real time. But there are some issues that we encounter because these scene graphs are built in real time and in real world. They're not necessarily always correct. So in the remaining part, what we'll discuss is how we can maybe come up with some learning-based models that can help us, that can help correct some of the mistakes that the Hydra or real-time 3D scene graph construction pipeline makes. And neural tree is one of the architectures that we propose, but in general, we would like to sort of come up with a discipline criteria, so as to say which model is a better model for correcting and learning over these 3D scene graphs. And GNN is a natural fit, but what more than a GNN? What sort of criteria should the GNN satisfy? How should we characterize expressivity of such graph neural networks? So that is the thing that I'll tackle for the remaining part of the talk. Yeah. So errors in real-time 3D hierarchical construction. So when you run this pipeline, you because it's run on the real world data, you end up getting few errors. So one is like you can get some of the node labels incorrect, and because your initial segmentation or object detection didn't work, and that error will filter all the way up to the scene graphs. You may have missing nodes because a robot traverses in the environment. It may miss to see a certain object correctly or with like enough degrees. So that will again percolate upwards to having a missing node in the scene graph. You can have issues where two objects get mistakenly clustered into one. This happens if you have like a low resolution of points when building a mesh. So if you have like small teacups sitting on a table very next to each other, they may get clustered into one. You can also have incorrect assignment of objects into rooms because of the hyperparameter for, say, the clustering algorithm not being set correctly, missing rooms and building labels because the robot doesn't understand like semantic information, and many more. So what we need going ahead is like having a learning-based model which takes in this 3D scene graph with errors and outputs a more corrected and a more complete 3D DSG. So and what we'd like to think about first is what should the learning model do? And one thing that we are sure of that what it should do is like it should enforce some sort of semantic constraints that a human sort of naturally knows. So for example, if you're told that a certain room is a bedroom, then it's very likely that it has a bed, or a kitchen very likely has a refrigerator. Or say if you're given a area in a room which has like a desk, chair, computer, and a lamp, you probably can say that it's most likely a study area. But these, more than just these univariate constraints, there are also like graph-like constraints. So let's say you have this figure with, let's say you have the scene where you know these bunch of few green labeled objects are chairs, but you don't know all the others. But because of the arrangements and the positions of the objects, you can sort of guess that the middle object should be a table and the other remaining object should be a chair, should be chairs. As well as for, say, this is a plan of a apartment, and you know all these other regions, what they are, say a bedroom, a laundry, a kitchen, then you can probably guess that the remaining two have to be a living room and a bathroom, and probably the smaller one is the bathroom. So so this is another instance where a graph-like constraint rather than just the simple univariate constraint come in handy. Similarly, the exploiting the hierarchical nature in the graphs. So if you're given another, say, a floor plan of, say, a level 2 of an office building, and if you're told that these are various office cabins, then because this is an office building, you can sort of deduce that the internal structure inside every office building should be almost the same. So these are the constraints that the learning model should enforce. And GNN seems like an appropriate model because it can induce correlation across different nodes in the graph because of the iterative message passing that it has. So what we need is a graph neural network based model that can enforce such semantic constraints. Now, these semantic constraints are obviously available in training data, and that is where the graph neural network model would learn them from. So an expressive enough graph neural network model should, at a high level, should be able to seep in all the semantic constraints and correlations from training data. So now to make this more concrete, we probably have to like go a little more deeply into how can we maybe mathematically write down what the semantic constraints and correlations may be. So how do we think of these semantic constraints? And one way to do it, and probably the only way to do it, because yeah, I don't know anything else. So so one way to do it is like inducing a probability distribution. So say, for example, you can say what the probability of bed is given a bedroom, and you can regress from the training data what this quantity might look like. And same way for, say, what the probability that you classify some area as a study area, given that it has a desk, chair, computer, and a lamp. And you can extend this to, say, graph constraints using what are called factor graph models. So factor graph models are basically probability distributions on graphs where every node in the graph is associated with a variable, and then there are factor nodes which sort of determine which other nodes are correlated. So you have a potential function defined for every factor, and the joint probability distribution is given by a product of all those potentials. And there are more than one way of writing an arrangement or a correlation in terms of factor graphs, depending on how much correlation you want to capture. Now, the 3D scene graphs that we have, we propose, like, the simplest way you can do it is by modeling them as a undirected graphical models. So in the undirected graphical models, unlike in the factor graph, the undirected graphical models dictate that the factors be the graph cliques rather than some separate nodes that are constructed. So in this case, so for example, this would be a clique, so there'll be a potential function for this clique, and so for every other clique. So for 3D scene graphs, or the hierarchical scene graphs that we have, so you'll have a bunch of cliques that go from building and a bunch of a building node and a bunch of room nodes, and a room node and a bunch of object nodes, and so on. So the joint probability distribution could be given by something that looks like this. And so this is what we would like to learn. So these are the correlations that we would like to, like our graph neural network model, to learn. So what we say is expressivity, we define it as the ability to approximate any such function. And we make a slight tweak for mathematical convenience, is that by we replace the multiplication with a summation, but you just take a log, and you can log of the probability, and you get this function, which we call a graph compatible function. So if a graph neural network on a graph is able to approximate any graph compatible function, we call it an expressive architecture. Okay, so how to build this? Now probabilistic graphical models are pretty old, and they've been used quite extensively, and where the state of the art in many cases till the deep learning methods arrived. And one of the methods to solve this was the loopy belief propagation. So the loopy belief propagation worked as if like you posited initial belief and some message that you pass from one node to the other, and you iteratively updated the beliefs and the messages by some equation. So for example, the message you would update by the belief at one of the edges, one of the nodes, and the previous message, and the belief in the next iteration you would update by aggregating all the messages that are incoming to it. Now this seems very similar to what a graph neural network is, and so it is. So if you just think of neuralizing this, like in the sense like replacing this function with a more generic f that could be modeled as a neural network, and same way for this g, then this looks very similar to what is known as like message passing neural network. And we know the expressivity, and there's an interesting parallel between these two, and that is the expressivity of this is limited by 2WL test. That is, it can distinguish between non-isomorphic trees, but not any graphs. And loopy belief propagation is also known to be not optimal for inference on general graph, except on trees. So there seems to be some nice parallel between the two. What inference models on inference algorithms on probabilistic graphical models have led to is like instead is what is known as junction tree algorithm, where instead of doing message passing on the original graph, you convert it into a tree graph where each node in the tree represents a clique, a clique or a bunch of nodes in the original graph and you do message passing on this. So the idea then is like, if loopy belief propagation is sort of parallel to a message passing neural network or a graph neural network on the original graph, then can we extract a similar parallel with the junction tree algorithm and get a more expressive architecture? And that is exactly what we do, and it's the idea behind neural tree architecture. So for the given input graph, we construct what is called an H tree. Now, H tree is different from the junction tree. We construct the H tree by successive tree decomposition. So we get a hierarchy of features rather than just one level of hierarchy in the normal tree decomposition. And we propose that you do message passing on this. So I don't have time to go through all the construction results, but what we show is like the expressivity claim that given any graph compatible function, the neural tree model is able to approximate to any arbitrary precision. And there's a nice complexity claim that we have, that it's the number of parameters that you need to approximate grows exponentially in the graph tree width. And graph tree width is another parameter that shows up in many combinatorial optimization problems, including in the graph isomorphism, which many people in graph neural network have also considered. Okay, so just showing one piece of result as to what the neural tree is able to do. So we took this 3D scene graph dataset, which is a nice dataset prepared by Stanford and Berkeley, people in Stanford and Berkeley, and we ran on multiple standard graph message passing on the original graph and on neural tree. And what you observe as you give it more training data, the prediction accuracy increases. So that is the expressivity of neural tree is high, but it's able to show it only if it has like enough training data to learn all the correlations. Whereas for classical graph neural network message passing, the average accuracy begins to taper off. So I guess I'll end here because it's like 5 minutes and open for question. But I hand over to Luca if he has like the final slide. Hello.
Okay, so thanks, Rajat. So let me close with this final slide. So in summary, in this presentation, we just argued that 3D scene graphs provide a general and expressive representation for hierarchical 3D scene understanding for robotics. And I spent the first part of the presentation talking about Hydra, which is a real-time perception system to construct 3D scene graphs from sensor data, again in real time. Probably the interesting bit is that Hydra is going to be open source during RSS, so it's going to be online on GitHub next week. And Rajat covered this idea of neural tree, which is essentially a new architecture for graph neural networks, which is drawing a parallel between graph neural networks and probabilistic graphical models. And through that parallel is also establishing performance guarantees, approximation guarantees of the neural tree applications, of the neural tree architecture. So of course, there are many challenges and opportunities here. A lot of the work I presented in my part of the presentation is really about doing bottom-up inference to construct a scene graph. And Rajat work seems to be like, more of a top-down processing, figuring out a way to properly couple these two top-down and bottom-up processes in a single inference approach is still an open problem to us. Figuring out how to do system-level monitoring and certify that the 3D scene graph produced by Hydra, for example, is correct is also something that we are interested in. And finally, the semantic segmentation we get in our meshes still relies on supervised learning and is currently the bottleneck. If you remember the videos that I was showing in the presentation, the 2D semantic segmentation is never perfect in practice. So we're looking into self-supervised approaches to figure out the semantics and that we can use to augment Hydra. And I will close it here. We'll just acknowledge the sponsors which are supporting this work, and I will thank you for your attention. Hopefully, there will be 1 or 2 minutes for questions.